Hello everyone. In this video, we talk about the expected value and the variance of discrete random variables. If the probability distribution function of a discrete random variable x is known, the expectation and the variance or the standard deviation of x can be compiled. The expectation can be regarded as the long-run average and the variance or the standard deviation as the measure of dispersion of the random variable. Similar to the definition of the mean and the variance of a dataset, the expected value of a random variable x measures where the probability distribution is centered, and the variance of a random variable x measures the amount of variability in the distribution of x. Let's take a look at the definition of the expected value. Consider a discrete random variable x with PDF p of x. The expectation, or we call as expected value or the mean of x, is denoted by mu of x or E of x. This can be considered as its weighted average over all possible outcomes, where the weights are the probability associated with each of the outcomes. So we have the expression of E of x equals x1, the first possible value of x times the weight, where the weight is the probability of the random variable x equals x1, and then plus the second possible value of x, say x2, times the associated probability, until we sum up the expression for all possible value of x. So we have expected value of x ex equals to the summation for all possible value of x of the term x times p of x. The mean of x can be interpreted as the average value of x in the long run. Let's take a look at a few demonstrations in computing the expectation of a random variable. Here we have a graph of p of x, where x can take on value 1, 2, 3, and 4, with probability 0.25 each. So the expected value of x equals 1 times 0.25, the first term, x equals 1. And then plus the second term, when x equals 2, we get 2 times 0.25 plus 3 times 0.25. And then the last term, 4 times 0.25, we get E of x equals 2.5. And then consider another random variable, say y. Y can take on values 1, 2, 3, and 6 with probability 0.25 each. Let's compute the expected value of y. We have 1 times 0.25 plus 2 times 0.25 plus 3 times 0.25, and then lastly plus 6 times 0.25, we get E of y equals 3.0. And then the last demonstration, the variable w can take on value 1, 2, 5, and 6 with the associated probabilities. So E of w equals 1 times the probability, which is 0.35, plus 2 times 0.15, and then plus 5 times 0.15. The last term is 6 times 0.35. We get E of w equals 3.5. You can see that the expected value of a random variable serves the role as the center of mass of the density function. Next, we move on to the variance. The variance of x, denoted by sigma square x or V of x, can be defined as the weighted average of the square discrepancies between each possible outcome and its mean. So we have V of x equals x1 minus the expected value or the mean E of x squared. So this term is the square discrepancy between the value x1 and the mean of x times the associated probability P of x1. Sum up the expression for all possible value of x, and we get this expression, the summation for all possible values of x of the expression x minus the expected value of x and then square times P of x. We can replace E of x by the symbol mu of x in the expression. Let's take a look at an example. So we have a PDF of x and the PDF of y. Compute the expected value. We get E of x equals 4 and E of y also equals 4. From the graph of the PDF, the dispersion of y away from the mean is greater than the dispersion of x away from its mean. So we can expect that the variance of y is greater than the variance of x. Let's compute the numerical measure. So V of x equals 2 minus 4 squared times 0.2. This term corresponds to x equals 2 minus the mean 4 squared times the associated probability at x equals 2. And then the second term, 3 minus 4 squared times the probability 0.2. We do the same for x equals 4, x equals 5, and x equals 6. And we get V of x equals 2. For the random variable y, the first term is 1 minus the mean 4 with a square times the probability 0.25. And then plus 2 minus 4 squared times 0.25 plus when y equals 6 and y equals 7, we get the last two terms. Upon calculation, we get the variance of y equals 6.5. So far, we have covered the expected value and the variance of a random variable. Another measure associated with the variance is the standard deviation, denoted by sigma of x. The standard deviation is a convenient measurement of dispersion in the same unit as x, the same unit as the unit of the random variable, where the standard deviation is defined as the square root of the variance. Let's take a look at an example. The following table gives the probability that X photocopiers are sold in a week according to the past record. So here we have the PDF. Compute the expected units of photocopier that will be sold in a week. So we need to get the value of E of X. So we have 0 times 0.05. So this corresponds to x equals to 0 multiplied by the associated P of x, in this case P of 0, 0.05. And then the next term corresponds to x equals 1 times the associated probability 0.22 plus 2 times 0.38 until the last term we have 5 times 0.01. And we get the expectation of x equals 2.15 unit. The expectation of x equals 2.15. So what is the interpretation of this value? On average, it is expected that 2.15 units of photocopiers will be sold per week in the long run. So for certain weeks, we will observe no photocopier sold in a week. For some other weeks, there may be 1 photocopier sold. And for some other weeks, there may be 2, 3, 4, or 5 units of photocopier sold. Let's compute the variance and the standard deviation on the units of photocopier sold in a week. So we have the expression for computing the variance of x. E of x equals 2.15. And so the expression, the first term, when x equals 0, we get 0 minus the mean, 2.15, square times the associated probability, 0.05. And then plus the second term, x equals 1 minus the expected value 2.15 square times the probability 0.22 until the end when x equals 5. We get the term 5 minus 2.15 square times 0.01. And we get the variance equals to 1.1275 square unit. And the standard deviation is the square root of the variance. So we get the standard deviation as 1.0618 unit. Okay, so we get all the required quantity. The expected value is 2.15. The variance is 1.1275. And the standard deviation is 1.0618. So what do all these numbers mean? So if you take a record, say in the future 100 weeks, for each week, you keep a record on the number of photocopiers sold. So you get 100 weeks of records. And then if you compute the mean, this should be close to 2.15, the theoretical value that we have computed. And the variance of these 100 numbers regarding the unit of photocopier sold should be close to 1.1275, and the standard deviation is close to 1.0618. That's it for today's video. Thank you for watching. In the next video, we will talk about the expected value of functions of a discrete random variable.